There are three main types of carbon capture methods: pre-combustion, post-combustion, and oxy-fuel combustions. In our project, we have chosen post-combustion capture as it is the most suitable for integrating with the existing chemical plants. It allows us to reduce carbon emissions without major process changes to the current operations. As shown in the slides, the process will begin from the flue gas pretreatment to remove sulfur dioxide. Next, the flue gas will enter the carbon dioxide absorption unit where the CO2 is captured. Then the captured CO2 will then go through a conditioning step such as purification or compression before being used for e-fuel productions. So in this case, we also want to explain why we don't use the direct air capture. While direct air capture method is possible, but it is much less efficient compared to the post-combustion carbon capture because the carbon dioxide concentration in air is only about 0.04% compared to 10 to 15% in the flue gas. Direct air capture also requires much more energy and cost, making the flue gas is a more practical and impactful source. Especially we know that over 80% of the carbon dioxide emissions is come from the fossil fuel combustions. This is the flue gas composition we refer from a journal source, and for our case, we assume the flue gas already undergone filtration, so no solid particulates remain inside the flue gas.
Now, I will be explaining the process of flue gas desulfurization, or we call SFGD, which is a critical method for reducing sulfur dioxide emission. So, we go to the functionality and the justification of this process, which is the first one will be the flue gas as a transport medium for SO2 and other pollutants. During the combustion of SO2 is produced and carried to the flue gas stream. This stream then flows into control systems such as scrubbers or dedicated FGD units for treatment. Secondly, FGD serve as a target for pollutant removal. The SO2 in the flue gas react with the chemical absorbents like CaO or limestone or CaCO3 calcium carbonate, which this reaction can happen in either wet or dry scrubbers. As a result, solid byproduct like gypsum, CSO4 2H2O are formed, which are then removed from the system. And then now we are take a look at the chemical equations that involve in this process, which is the first one will be the lime react stage with limestone reacts with water, which CaCO3 will be dissociate, become ion, positive and negative. Number 2 will be the scrubber, as SO2 reacts with water to form bisulfite ions, which is HSO3 minus, as well as bisulfite ions will further oxidize to sulfate. And then the last one will be the GCR step, will be calcium ions react with the sulfate ions to form the gypsum, as I said, which is the CaSO4 2H2O. Through this multi-step process, harmful sulfur dioxide or SO2 is effectively removed from the emission and converted into useful gypsum, which can be repurposed, for example, in construction materials. So we proceed to the advantage of the flue gas desulfurization. So the advantage of the flue gas desulfurization, we got 6 here, and the number 1 will be the reduces of air pollution as well as protecting the environment, which is in the study in the research effectively remove up to 95 to 99% of sulfur dioxide SO2 for the flue gas, which is significantly reducing acid rain and smog formation. And number 2 is improve public health, which is reduces respiratory and cardiovascular diseases caused by SO2 and fine particulate emission. Number 3 produces useful byproduct, which is generates the gypsum as a byproduct that we can use in the construction, or we can use as a wallboard or the plasterboard. And then number 4, regulate compliance, which is helps power plants and industry meet environmental emission standards and avoid the penalties. And number 5, supports cleaner energy transmission, which is allow continued use of existing fossil fuel infrastructure while reducing environmental impact during the transition to renewable. And the last one will be boost industrial sustainability, which is enhance the company environmental responsibility and corporate ESG profile. So we go to the next slide. We move on to the process design unit of the flue gas desulfurization. So the flue gas desulfurization, as you know, a critical method used to reduce sulfur dioxide, or we call as SO2 emissions from the flue gas. And then we looking forward to the process that will begins as flue gas indicated as S1 FG enters the system through the preheat section. This prepares the gas for optimal contact with the scrubbing medium. Next, calcium carbonate or CaCO3 together with water H2O is fed into mixing unit to form a slurry. This reaction occurs in the lime DS unit where the CaCO3 dissociated and become active for the desulfurization reaction. And then the next unit will be this. I will talk about the scrubber reaction, which is the slurry is then introduced into the scrubber. Here is a crucial chemical reaction takes place when the sulfur dioxide in the flue gas reacts with calcium carbonate to form calcium sulfate, which later converts to the gypsum. And then this is the heart of the SO2 removal process and where the SO2 removal objective starts. Okay, so we go to the gas solid separation, gas SP, which is after scrubbing, the gas mixture enters the gas SP unit. When here, we will obtain the clean gas by assuming NOx level are traced, which is will separate and exits at the top stream. Meanwhile, the gypsum byproduct settles towards the bottom for further processing. And then we go to the gypsum. When the separated gypsum flows into this gypsum unit, where it exists primarily in solid liquid phase. This byproduct is now ready for final dewatering. And then last one, gyps SP. In the gyps SP stage, a final separation occurs, which is the solid gypsum is removed, and then the remaining liquid is discharged, and then this results in usable gypsum as a byproduct and minimize liquid waste. So all in all, to summarize, what I gonna tell, I explain this, which is the FGD is process that effectively remove the SO2 by reacting it with CaCO3 or calcium carbonate in a scrubber, separating the clean gas and recovering the gypsum in a solid liquid separation process. And then before we go to the absorption and desorption, this technology plays a vital role in reducing air pollution and promoting industrial sustainability. So we go to the absorption and desorption.
I will handle the carbon dioxide absorption and desorption process. So the carbon dioxide from the flue gas is absorbed into a solvent in the absorber column and then released in the stripper through heating. The clean flue gas is discharged and the solvent is recycled for continuous operations. In our case, we use the monoethanol amine MEA as the solvent. So you can see that on the left side are the main kinetic reaction showing how the MEA reacts with the carbon dioxide. On the right side are the side equilibrium reactions, including the water dissociation and carbonate formations. There are also a note on reaction involving sulfur compounds, which may occur if a hydrogen sulfide is present in the flue gas. In our project, we chose absorption as the carbon dioxide capture method, and here is the reason. Absorption is the most mature and widely adopted technology for post-combustion carbon dioxide capture. It handles high gas flow rates efficiently, like our case of 100,000 tons of carbon dioxide per year. It also offers flexibility with solvent choices such as MEA, MDEA, or their blends. Because of absorption has high high reaction kinetics and also good mass and heat transfer property, it is ideal for large-scale applications. We did consider other methods, but they each have significant drawbacks. For example, the cryogenic separation requires complete removal of water to avoid ice formation, and it comes with very high refrigeration costs. For the membrane separation, it has low efficiency for flue gas, especially due to its low carbon dioxide concentration. So the membrane separation is better suited for smaller flow rates. For the adsorption, it is very sensitive to moisture in the flue gas and also offers limited capacity and low selectivity for carbon dioxide. So based on these comparisons, absorption is clearly provide the best balance of efficiency, scalability, and practicality for our applications. Here I will explain why we choose MEA. So the MEA we choose is at 20 to 30 weight percent, and MEA is actually a primary amine commonly used in post-combustion carbon dioxide capture. It offers fast reaction kinetics, high water solubility, and is more cost-effective than the secondary or tertiary amines. MEA show extremely high carbon dioxide removal efficiency from 87.1 to 100%, and the MEA is well established in the industrial applications, especially in power and chemical plants. However, there are some considerations during we choose the solvent. First, the MEA will degrade over time, especially in the presence of oxygen, sulfur dioxide, or nitrogen oxide. And it also requires relatively high regeneration energy, around 3.8 to 4.8 gigajoule per ton of carbon dioxide. So to address these issues, we include the flue gas treatment to remove the sulfur dioxide, and we also apply the heat integration between the hot lean solvent stream and also the cold rich solvent stream to reduce the energy consumption. So look at these experiment simulations. The carbon dioxide absorber is the central unit where the flue gas comes into contact with the liquid solvent to remove the carbon dioxide. As the flue gas rises through the pack column, it reacts with the solvent flowing downwards, allowing up to 90% of the carbon dioxide to be absorbed efficiently. Above the absorber, a water wash section is installed to minimize the solvent loss. This section will spray the clean water to capture any solvent vapor and before the treated flue gas is released to the atmosphere, reducing the environmental emission and solvent consumption. To compensate for the solvent loss over time due to degradations or evaporations, a makeup MEA stream is added to maintain the desired solvent concentration and system performance. Then the absorbed carbon dioxide stream will go to the MEA stripper. The MEA stripper is where the carbon dioxide is extracted and the solvent is regenerated. Heat is applied to release the pure carbon dioxide from the solvent. Then we want to improve the energy efficiency, so a lean rich heat exchanger is used to transfer heat from the hot regenerated solvent to the incoming carbon dioxide rich solvent. This can reduce the reboiler steam requirement and also improve the overall process sustainability. Here is the design summary of our absorber and stripper columns. So for the absorber, it operates at 40 degrees Celsius and 1 bar using a 10 meter pack column with Melapack 250X. The design aims to remove 90% of carbon dioxide from the flue gas, and the calculated diameter based on the rate-based modeling is 1.25 meter. The MEA stripper uses Melapack 250Y packing and operates at a reboiler temperature of 120 degrees Celsius and 1.8 bar. With a condenser is at 10 degrees Celsius. It's designed to produce 100,000 tons of carbon dioxide per year at 99 weight percent purity. And the column we design is 9 meter high with a calculated diameter of 4.33 meter. So in our case, we use structural packing to maximize the contact area and avoid liquid channeling. So this can enhance the overall absorption and desorption efficiency.
Next, I will be presenting on CO2 conditioning through open cycle liquefaction with multi-stage expansion. This is a key method used to prepare carbon dioxide for storage or transport in a liquefied tone. The primary purpose of this process is to liquefy carbon dioxide by reducing its temperature and pressure in stages. Liquefied CO2 is much easier to store or transport, especially in carbon capture and storage projects. In an open cycle system, carbon dioxide itself acts as the working fluid. There is no external refrigerant, and unlike closed-loop system, the carbon dioxide is not fully recycled. Instead, it passes through compression, cooling, and expansion, and the liquefied portion is collected directly. Next, let's walk through the key process steps in the open cycle liquefaction. First is compression. The carbon dioxide gas is then compressed in multiple stages, raising the pressure. Next is cooling. Carbon dioxide is first cooled to remove the heat after the compression. Next is multi-stage expansion. After that, carbon dioxide is expanded in 2 or more stages, lowering both its temperature and pressure. Lastly is the phase separation. As it cools, liquid carbon dioxide is separated from vapor and liquefied CO2 is collected. Advantage of this method is it's relatively simple in design, and more importantly, it is cost effective since it doesn't require any external refrigerant system. Now let's look at how this is modeled in Aspen. So the first stage is pre-liquefaction conditioning. It is where the carbon dioxide feed is adjusted to the target pressure and temperature before entering the compression stages. Next is compression cooling stages, where the carbon dioxide is compressed from around 16 to 85 bar. This happens in multi-stage compression, with intercoolers in between to maintain a constant 30 degrees Celsius after each stage. So why is this important? It keeps the energy demand low and prepares the carbon dioxide for efficient cooling in the next stages. Next is multi-stage expansion. After compression, carbon dioxide goes through these stages, typically from 85 bar back down to 16 bar, and each expansion leads to a temperature drop, eventually reaching around negative 26 degrees Celsius. And during this partial condensation occurs, meaning part of the carbon dioxide turns into liquid. And lastly, final drums are used to spread the liquid CO2 from the vapor, improving liquefaction efficiency. For the last stage is the final liquefaction stage, which is at 16 bar. The carbon dioxide is further cooled to about negative 26 degrees Celsius to complete the liquefaction. So this will give us pure liquid carbon dioxide, and it's ready for storage or pipeline transport.
So for the e-fuel synthesis from carbon dioxide and hydrogen gas, so the method that we choose is subverted process, which is also known as revalidation. So the temperature for this process is 550 degrees Celsius, pressure 4 bar, and the catalyst used is nickel and aluminum oxide. From this process, we get a 100% conversion of carbon dioxide. So the main reaction for this process is carbon dioxide plus hydrogen produces methane gas and water. So the enthalpy change is negative 165 kJ per
Synthetic Flue. So this process uses a very expensive nickel catalyst and basically alternated by plutonium and rhodium. Next is the one reaction conditions. This process operates efficiently at ordinary temperature and pressure, simplifying the design. Next is a high efficiency process. achieves a high carbon dioxide component and maintains selectivity. Next one is the proven technology. This process is a well-established state and space application ensuring reliability. The last one is better integration. This process is easily combined with hydrogen production and carbon capture systems. So the main equipment used for the e-fuel synthesis is the reactor, which is a catalytic reaction that converts carbon dioxide and hydrogen into methane and water at 550 degrees Celsius and a pressure of 4 bar using the nickel-based catalyst, nickel aluminum oxide. The next one is the flash separator, which works at 4 bar and 70 degrees Celsius, separates methane and water.
This is our plot flow diagram. So let me walk through our process. We start with the flue gas desulfurization reactor, where calcium carbonate solid and water are added. So the output is a slurry which goes into the scrubber, and in the scrubber, the slurry reacts with the incoming flue gas, and then it goes into the separator and then splits the stream, sending the clean flue gas to the absorber and liquid waste to the cyclone. The cyclone removes a gypsum as a solid product along with a liquid stream containing water and dissolved SO2. Next, the clean flue gas enters the absorber where MEA solvent is used to absorb the carbon dioxide. The output is unreacted flue gas, pure CO2, and water. The pure CO2 gas is then compressed and then sent to a liquefaction separator. In the separator, gaseous CO2 is cooled and liquefied and ready for conversion. So it is then sent to a mixer where it is combined with hydrogen gas. Then the mixed gas enters the Sabatier reactor where CO2 and hydrogen react to form methane and water. Finally, the stream enters a separator producing two outputs, methane and hydrogen gas from the top and liquid water from the bottom.
So this is the drawing of the process flow diagram of the flue gas desulfurization. This will be the drawing of the PFD of CO2's capture. Next, this will be the drawing of the CO2 conditioning, which is we want to change the phase of the CO2. And then the last one will be the e-fuel synthesis. This is the drawing of the e-fuel synthesis where the liquid of the carbon dioxide, we will get the desired product, which is the methane gas at the top stream. So we proceed to the overall PFD. So this is the overall PFD. If the photo is a blur, you can scan the QR code and can zoom the detail of the overall PFD.
So let's look into the material safety data sheet of the components used in this process. First one is methane. The boiling point is negative 161.48 degrees Celsius. Flash point is negative 104 degrees Celsius and the auto ignition temperature is 537 degrees Celsius. It is a gas state, colorless and odorless gas. Next is carbon dioxide. The boiling point is negative 56.6 degrees Celsius. It exists as gas, colorless and no odor or night property. Next one is hydrogen. The boiling point is negative 253 degrees Celsius and the auto ignition temperature is in between 500 to 571 degrees Celsius. It exists as gas. Hydrogen gas is also colorless and odorless gas. Next is the point is 167 degrees Celsius. Flash point is 9.5 degrees Celsius and the auto ignition temperature is 424 degrees Celsius. It appears as a clear liquid, colorless and odor like odor. Next is the carbon monoxide. The boiling point is negative 191.52 degrees Celsius. The photo ignition temperature is 600 Celsius. It is in gas state, colorless and odorless gas. Next one is water. The boiling point is 100 degrees Celsius. The physical state is liquid at room temperature and colorless and odorless. Next one is nitrogen. The boiling point is negative 196 degrees Celsius. The physical state of nitrogen is gas, is a colorless and odorless gas. Next is the oxygen. Oxygen, negative 183 degrees Celsius. The physical state is gas. Oxygen is a colorless and odorless gas. Next is nitrogen dioxide. The boiling point is 21.2 degrees Celsius. The physical state is gas with the color of reddish brown. It has an odor of pungent and acidic odor. The last one is sulfur dioxide. The boiling point is negative 10 degrees Celsius. The physical state is gas. The color is colorless and have the odor of choking, suffocating, pungent, acidic odor. List of equipment used in this project. First one is the heat exchanger. The type used is shell and tube heat exchanger. It is used for the heating and cooling processes streams by transferring heat between fluids. Typically applied to preheat feed stream, recover heat from hot processed fluid, and to regulate temperature before entering reactors and other equipment. Next is the splitter or mixer. The type used is static mixer. The function is to combine two or more process streams into single uniform stream to ensure proper mixing of components before further processing. It divides a single process stream into more separate streams used for distribution to different units of process sections. For the next, pressure changer. The type used is centrifugal pump and centrifugal compressor. Centrifugal pump is used to transfer liquid streams by putting rotational energy into fluid flow, ensuring steady circulation and maintaining required pressure in the system. The centrifugal compressor is used to compress the gas streams, increasing the pressure of carbon dioxide, hydrogen gas to meet the required operating conditions for efficient reaction and separation. So the next equipment is the reactor. So the type of reactor used is fixed bed reactor and CSTR reactor. So the fixed bed reactor is to ensure the gas flow through the packed bed of the solid catalytic particles. It is used for catalytic gas-phase reaction like methanation and reforming. So the next one is the CSTR, which continuously mixes the reactants to maintain the uniform condition, making it suitable for steady methane production from carbon dioxide and hydrogen. So lastly, the equipment is backpack column, backpack exhauster and shaping column. So the function of the backpack column is to separate and remove impurities such as sulfur dioxide and nitrogen dioxide from the synthesis gas stream. So the backpack exhauster and stripping column is to use to remove the flue gas from the feedstock before it enters the reformer and to remove the impurities or the unwanted components from the hydrogen stream.
This slide summarizes the utility requirement across our carbon dioxide capture and e-fuel production process. We use electricity, cooling water, chilled water, and steam throughout the plant. For electricity, the main consumers are the e-fuel cooler and also the feed heater, followed by the compressors in the CO2 conditioning. Now the second part of the utility list. So going to the cooling water and chilled water, they are served for different temperature needs. For cooling water is typically used to cool down the stream to moderate temperatures around 30 to 40 degrees Celsius. For example, is used in the MEA cooler and also the water wash cooler. For the chill water, it is required when lower temperatures are needed, usually is below the 30 degrees Celsius. So a major usage is in the MES stripper condenser, which operate at 10 degrees Celsius, require over 49,000 kilowatt of chill water duty. Lastly is the steam. Steam is used for solvent regeneration in the stripper reboiler with a duty of around 57,000 kilowatts, which is expected because the thermal energy required for desorption.
So what we are going to do for the next semester, that we want to add some reaction, which is the suggestion that we are going to do for the next semester will be selective catalytic reduction, or we call as SCR. And the location where we want to put this reaction reduction, um, or we call as SCR, is after the flue gas desulfurization, and then the flue gas without the SOX will flow into this reaction. And then as you can see here, there are three main basic reaction mechanism with ammonia, which is we are trying to mix the flue gas as well as the ammonia to reduce the NOx, which is the first one will be NO, nitrogen monoxide. The second one will be nitrogen dioxide, or nitrogen monoxide plus nitrogen dioxide, which is we mix together, and then we got the product mainly is nitrogen gas as well as the H2O. And the SCR is actually the selective catalytic, which is we are using the catalytic, which is the vanadium pentoxide V2O5, with supported of tungsten oxide TiO2 and titania, which is WO3. So other than that, we are trying to find the research paper that say about the zeolites as well as the iron or the copper zeolites. And then this will be our research for the next semester. And then we go to the next slide. As you can see here, the left hand side will be the efficiency of the NOx removal according to its temperature reaction, and the right hand side will be suggestions of what we gonna do, or the reaction that will take place during at this selective catalytic reduction, which is the SCR.